So here you have a diagram explaining all the particles that we know, so everything that constitutes the matter around us. They come in two different types. On one side you have what we call the fermions, so this is everything we can touch. And on the left here you have everything that you have the bosons, and this mediates all the interactions between the fermions. And you have one particle here is very special, called the Higgs boson here, and interacts with particles proportionally to their mass. It's the only interaction that allows us to distinguish between these different types of particles, because they have very, very, very different masses. Here you have a picture of the results from the ATLAS and the CMS collaboration that shows you all the interactions we measured so far. So what's also very interesting about this plot is that you can see what's missing. And one thing that you can notice here is that at this place here you have a space, and here is where the charm quark should come. And this interaction we haven't measured yet. And this is what we're trying to find out in my thesis. We're trying to measure the interaction of the Higgs boson with charm quarks. The way we do this is that we collide protons at the center of the ATLAS detector at the LHC at CERN. And then we're looking for events where a Higgs boson is produced in association with a Z boson. And so what we're trying to do here is to measure these final states and then infer the properties of the Higgs boson from this measurement. The way it looks like in the data is a bit more complicated. You can see it here. And what's very interesting about this event is that actually it was a real event measured in 2018, and I was in the control room of the ATLAS experiment to measure it. So the first result I want to show here is basically the mass of the Higgs boson candidate. So here you see some events that we reconstruct in the ATLAS detector, and you can see some simulation that compares to it. And you can see here the mass of the two jets, so the two quarks, and so it should peak at 125 for the Higgs boson. And then you can see here at 125 we have some Higgs boson events, or some candidates. They're not peaking a lot, but we can see that we can put some constraint on this kind of process. And the main result of this analysis is that we measure that the Higgs boson process should happen less than 26 times the prediction of the standard model. And this is the best limit so far in the world. Of course, we didn't measure the Higgs boson decay to C quarks, but can we say something about its interaction with C quarks? And we're trying to test, for example, if the Higgs boson decays to C quarks as often as it decays to B quarks. And if that was the case, then it would happen at this line, green line here. And what you can see is that we're actually able to exclude this line, and we're actually able to prove with the data that we collected in ATLAS that the Higgs boson interaction with C quarks is weaker than with B quarks. And here you have a summary of all the measurements that happened so far. And now you see these results of my thesis here with the best constraint on the Higgs boson decay to C quarks, which is 26 times the standard model. And of course, what's exciting here is that we're going to be able to probe more and more the interaction of the Higgs boson with C quarks. And this is going to allow us to really search for new physics with the interaction of the Higgs boson to C quarks.